So it's time to play Name That Derivative. Now, I used to do this differently, but for today, I knew we were going to be short on time, so we're going to kind of skip some of the formalities and jump to the end. So here's what I've got. This first table, so the function f of x equals x squared, I have in this column the x's, and I have in this column the derivative values, or the slope of the tangent at that point. So for example, the derivative of x squared at x equals 1 is 2. The derivative of x squared at x equals 2 is 4. The derivative of x squared at x equals 3 is 6. In general, I hope you can tell that we're just doubling every time. So the derivative of x squared at x equals a is 2a. You just double the x. Suppose y equals x cubed. Well, this one's a little harder. The derivative at x equals 1 is 3, but the derivative at x equals 2 is 12. And the derivative at x equals 3 is 27. So it's not just like 3 times. What is it? It actually ends up being 3 times the x value squared. So if we take 4 squared, we get 16. 16 times 3 is 48. So you square the x value and times it by 3. If y equals x to the 4th, you go through, you get all your numbers. In the end, what we do is we take 4 times the x value cubed. So take a look at this for x squared, this for x cubed, and this for x to the 4th. In your groups, I want you to think in general. If y is x to the nth power, can you figure out a rule for the derivative of that function? In your groups, talk about it for a minute.
So you bring the power to the coefficient.
Did y'all figure it out? Yeah. Tommy, what'd you guys get?
We just said you bring the power to the coefficient.
Okay. And then subtract 1 from it. So n x to the n minus 1?
Yeah.
Beautiful. Anyone else get the same thing? Yes? Yeah? Okay. That's correct. Well done. So that has a name. But before I tell you the name, I have to put you in suspense because I got to give you the intro slides for the chapter. So this is chapter 3. Chapter 3 is all about differentiation rules. These are shortcuts. Most of this chapter, but not all because there's a lot of application, but most of this chapter is learning how to find derivatives using shortcuts so that we don't have to do the limit definition every time. Because in all honesty, the limit definition can be rather cumbersome, especially once the functions get complicated. So in order to save ourselves an enormous amount of time, mathematicians have created some rules that are basically shortcuts for finding derivatives. So the first several lessons of this chapter is just learning all those shortcuts. Okay, so today, lesson 3.1, we are going to learn the derivatives of polynomials. We're going to use, that's power rule that we're about to learn. And we're going to learn how to find the derivatives of simple exponential functions, meaning all we're going to learn today is e to the x. We're going to learn the derivative of e to the x today. Okay, so power rule. It's called power rule because it deals with powers, meaning exponents, but I like it because I also think of it as the most powerful rule that you learn when you're in calculus. There is no rule that you will use more than this one. So the derivative of x to the n is nx to the n minus 1. Now, oh, yes?
So is d to the y over d to the x, is that just f prime?
Yes. Do you guys remember? It's been over a week since I showed you, and we never really talked about it again. Different notation for derivative. One way of saying y prime is to say dy dx. So y prime is more Newton notation, dy dx is Leibniz notation, but they all mean the same thing. Dy dx means derivative. Technically means the derivative of y with respect to x. Okay, so I'm going to have you do these three in your groups in just a moment. Before you start, I'll give you a little caution. Does this rule say x to the n, or does it say 1 over x to the n? It's not a trick question. It just says x to the n, right? Does it say the square root of x to the n? No. All it says is x to the n, which means anytime you want to use this rule, you had better have your function written as x to a power. Not 1 over x to a power, not the cube root of x to a power, literally just x to a power. So I'm going to give your groups a minute. For each of these, I want to see if, especially for these two, if you can rewrite the function as x to a power and then apply power rule. So take a minute, see if you can work these out. You might also want to take a moment and introduce yourselves because you have new groups, right? Learn all your names.
Alright, my name is Ari Cohen.
I'm Karen. So for the third one, I'm really writing it.
I'll show you anyway. All right, so for this first one, woo! All right, so just as a class, what's the derivative of x to the 7th?
7.
Good job, class. Well done. Okay, so Ryan,
Yes.
how are you?
Pretty good.
Pretty good. All right, Ryan, and it's a lovely Hawaiian shirt, by the way.
Thank you.
Okay, so thank you. It's my husband's. I don't own any. I always just dig into my husband's closet for this stuff. Okay, so for this, let's see, power rule. So I would get 1 over 5x to the 4th, right? You're shaking your head. But I just did what it said, right? Nx to the n minus 1.
You have to think it so it's not 1 over.
Okay. All right. So this is the same thing as what?
Y is equal to x
X
to the negative 5th.
to the negative 5th. Do you all know 1 over x to the 5th is the same as x to the negative 5th? So you got to have your function written as x to a power, right? Not 1 over x to a power, x to a power. So now, Ryan, what's the derivative?
Negative 5 times x to the negative 6.
Ooh, very good. And you knew negative 5 minus 1 was negative 6. That's awesome. You think that that's like silly, but it's so easy to mess up with your negatives, right? So be careful when you're subtracting your negatives. Do you think I would accept this answer? You know, I probably would accept your test in the directions. There's like a paragraph at the top of your test. And one of the things in the directions of the chapter 2 or chapter 3 test is no negative exponents. Haha. So, how am I going to rewrite this?
1 over negative 5x to the 6th.
Okay, so Ryan
Negative
said,
5, negative 5.
oh, he's redeeming. Isn't it fun when you can redeem yourself? Okay, so Ryan started to say this. What was wrong with this?
Negative 5 isn't part of the other.
Right. The negative 5 doesn't have a negative exponent on it, right? This negative 6 only goes with the x, not the negative 5. So the negative 5 actually has to stay on top. So you get negative 5 over x to the 6th, and now we're happy. Good. Ari, how are you?
I'm doing well.
Good. Can you write this one as x to a power?
Would it be x to the 2/3?
I don't know. Would it be? Is that a statement or a question?
That's a statement.
That's a statement?
It's x to the 2/3.
It is x to the 2/3. Very good. You got it. All right. Whenever you've got radical stuff, power goes on top, root goes on the bottom. right? Power over root. Think P comes before R, power goes over root. Okay. All right. So now we've got x to the 2/3. So Jennifer.
Yeah.
Hi.
Hi.
So I've called it y prime and called it, oh, okay, I'm gonna use notation here just to freak you guys out. Okay. What does that notation mean? Just means the derivative of x to the 2/3. Like think dy dx. I just took the y and kind of put it next to the d dx. And what is y? It's x to the 2/3. Okay. All right, so d dx of x to the 2/3. All right, Jennifer, I'm ready. What is it?
2/3 over x to the
Okay, let's start just in general. First, when we subtract, we get x to the
-1.
-1/3, right? 2/3 x to the -1/3. And so Jennifer was jumping to the next step, which is take that negative exponent, put it on the bottom. So be careful. Top stuff stays on top. Bottom stuff goes to the bottom. So you can write it like that, and I would be okay with that. Just know in your homework, it's very possible that your book is going to put it back in radical form. So be comfortable going back and forth between exponential and radical form. Are we okay with this? This is nothing but like algebra 2 stuff, right?
It's been a while. Yeah.
Well, after your homework tonight, you'll get comfortable with it because you're going to have a lot of these. All right. Okay, we got to move on though. So constant rule. Name, let's see. Wait. Anthony. Hi, Anthony. Name a constant. 1. So y equals 1 is called a constant function. It's a function that is nothing but a constant, right? Anthony, what does the graph of y equals 1 look like? You can ask a friend, right? Hi.
Hi there. Hi, you guys. I don't see. Well, I'm looking for the owner of this jacket. She's not in class. She must be in orchestra.
Is that Twee Ian's jacket?
No, that's Emma's.
It's Emma's. Yeah, she's at the orchestra thing.
Is it with all the other kids?
Yes.
You have some kids in your class.
Yeah, I know, but it probably, how many are gone? Like 8 of them? Yeah, there's a lot.
Yeah, I'm missing like half of my class.
Yep.
Like next thing you know, cross-country runners will probably try and get out of class. Not that I would know any cross-country runners and stuff like that. So, y equals 1?
Yes.
How's that possible?
Oh my goodness. We're trying to figure out what the graph looks like.
I don't know. I don't want to begin to start thinking how to do that.
Oh,
Thank you.
all right. Thank you.
Recording was slow down.
Oh, that's okay. All right. Okay. So y equals 1 has a graph of what? A horizontal line, right? What does the derivative give you in one word? Slope. What is the slope of this line? Anywhere on the line? 0. So what about if I graphed like y equals 5? Would that be different?
No.
Same slope, always 0, right? Okay, so whenever you have a derivative of a constant, the derivative is always 0. Yes, like there are at least 8 problems on the test where you have to differentiate constants. Yes. Yep, and the test only has 10 questions, so you've already got like 80% of it. Okay. Do you really think I'm telling you the truth right now?
I'm not complaining.
Yeah, sorry.
Wait, so are constants just whole numbers?
No, constant is anything that doesn't have a variable with it.
Oh. Okay.
Yeah. So anything where it's not times x. Like if I said, hey, y equals 2x, now all of a sudden you've got a different slope that's not just 0.
Got it.
Yes, good question. Nisha.
Yeah. So instead of showing like our work on a test, now we can just say it by the constant rule.
You don't even have to say that. Believe me, there's gonna be, you're on like part 1, day 1. You're learning like the easiest nuts and bolts rules. We're not even close to problems that will be on your test yet.
Oh.
Yeah. So no, you will never have to state the rules. You'll just do the derivative. Okay, so 2 more quick rules. I do not like the name of this rule. It's called the constant multiple rule. It makes you, I have students all the time who, so if y equals a constant times a function, then y prime is the constant times the derivative. So, for example, if y, well, we're going to do examples in just a second. I don't like that name because students see a constant and they think, oh, constant goes to 0, when it's not really a constant if it's attached to a variable, it's a coefficient, right? I would prefer to call this the scalar multiple rule because I like to think of coefficients, numbers that are in front of variables. I like to think of them as scalars, not constants. But anyway, but this is the name that is used like by everybody. It's in every textbook. It's called the constant multiple rule. So we will give it to you because that's what it's called. Just know that C, yes, C represents a constant, but this is not a constant function. It's a function that's been multiplied by a constant. Okay. Sum difference rule, if you have sums of functions, you just do their derivatives and add them together. So I'm going to walk you through one problem, and then you are going to do the next 2 problems. So problem number 1, I've given you y equals 5x to the 7th, and I want y prime. I'm going to walk you through this because I want you to know how my brain works these problems. So this is technically a combination of the constant multiple rule and the power rule. So it's 5, don't write this. Like if I were to rewrite this, so my derivative would be 5 times the derivative of x to the 7th, right? So I get that 35x to the 6th, right? So the constant, the multiplier just comes along with the derivative. So multiplier times function, multiplier times derivative. Here's how I do them. So don't do that. My brain, when I do a derivative with a coefficient, which most of them have, is I think exponent times coefficient. So 7 times 5, and then reduce the exponent by 1. You're going to do so many derivatives that you're going to want to kind of build that habit. So exponent times coefficient, and then reduce the exponent by 1. So take a minute in your groups. Find the derivatives of the next 2 problems. I give you 40 seconds. The second one, we got, there we go. 35x to the 6th minus 24x squared. All right, and Nitty. For number 3, what did you get?
35x to the 6th minus 24.
Wait a minute. That's the same as this one. Are you saying these 2 completely different functions have the exact same derivative? Is that possible? Okay, let's think why. So, what is the difference between the graph of this? If say I started with this graph and wanted to generate this graph, what would I do?
Shift higher.
This would just be shifted 12 units up, right? So I want you to think about this. What does the derivative give you? What does it give you?
Slope.
Slope. So if I take the same graph and just shift it vertically up, and say I plug in some x value, is the slope different? Slope's exactly the same, right, on either graph. A vertical shift does not affect the slope at any x value at all, right? Horizontal shift does, because now your x values are different. But a vertical shift, you're going to get the exact same slope, right, no matter where you are vertically. Does that make sense? So when you have 2 functions and they're only different by a constant, they're going to have the same derivatives because one's just a vertical translation of the other. Good. See, you all need vertical shit. See, you remember stuff, right? You say you don't, but you do. Okay, this one's a great one. I think we have time. All right, so I give you 30 seconds to copy it, and then 40 seconds to differentiate it. All right. Huh. How are you? Good. Glad to hear it. There are two terms in this beautiful function that have to really be kind of rewritten before we can differentiate. Tell me one of those terms. 2 over root x is one of those terms. How would you rewrite 2 over root x?
2 times x to the negative 1.
Very good. Why negative? Because it was on the bottom, and then why 1/2? Because the square root, right? Do you guys know square roots are the only ones where the actual root is invisible? It's a 2 here. Okay. All right, good. So I'm going to replace this with this. Good. Keegan.
Yes.
What's the other term? Fifth root of x. How would I rewrite that? X to the 1, not negative?
No.
Are you sure? The other one was negative and it had a root. Ah. Okay. You positive?
I'm pretty positive.
Good.
That was a good one. Are you positive?
Oh, yeah. I didn't even pick up on that one. Oh, that's good. Okay. Oh, I love those math pens. Okay. So, here's Anna.
Yeah.
How are you?
Yeah.
Are you ready?
Yeah.
You're going to walk me through the entire derivative. If you get stuck, you can ask for help, okay?
Okay.
Okay, here we go. First one.
40x to the 7th
40x to the 7th, beautiful.
minus 12x to the 3rd
Minus 12x to the 3rd, you are perfect.
plus 12 over the cube root of x.
So you're, okay, so let's see. So this is where we had our first little hiccup. So it's 8 times 2/3, right?
Yeah.
So I think you did 8 times 3/2. We need to do 8 times 2/3, right?
Oh, yeah, so 16 thirds.
There we go. Good. 16, and I'm not even gonna clean it up yet. This would be x to the negative 1/3. Good. What's the derivative of 6x?
Is it 1?
Okay, so there is an invisible 1 here. So you do 1 times 6, which is 6, x to the 0 power. What is x to the 0 power?
1.
So you end up with 6 times 1, so you just get 6. So whenever you have a number times just x, the derivative is just that number. It's just that coefficient. So just think 1 times that number times x to the 0. You're doing great. Okay. You are. You're doing wonderful. Okay, next one. Ooh, x to the 1/5.
The 5th root of x.
Okay, walk me through the derivative without simplifying. So what would go in front?
It would be a 1/5.
Yeah.
Oh, wait, never mind. Yeah, it's 1/5 times x to the negative 4/5.
Negative 4/5, right? You're gonna be so good at fractions when you walk out of this class. All right. Okay, you're almost there. Okay, tell me this one.
Negative 1x to the negative 3 over 2
Oh my gosh, that was perfect.
plus 0.
And you nailed the constant. She nailed it. So, well done. That's a big problem, right?
Yeah.
Right? You should be tired.
Yeah.
You did it. So good job. All right, what's your question?
So the plus 6,
Yes.
will we need to incorporate that even though it's moving the graph up and down?
No, this isn't the graph anymore. What is this? This is the slope. The slope is changing by 6, not the graph, right? This is a constant. This is not a constant, right? This guy goes to 0. this guy goes to 6. This does affect the slope. Okay.
So I have an additional.
Yes, go ahead.
So derivatives are the instantaneous slope, right?
That is correct.
So what's this the instantaneous slope of?
So this is a function that gives you the slope of this curve at any value of x. So if I want the slope at x equals 2, I plug in a 2 for all of my x's and I get out the slope at x equals 2. Yes, good questions. Okay, Alec, what's your question?
When we're showing our work, do you have to say that we made constant zero?
You can just leave it off. And that is a fair question as well. Yeah, you do not have to write the plus 0 for the constant. Now, technically, we do have to rewrite these little negatives. For time, I'm just going to very quickly just write them below, and we'll pretend that we wrote the whole thing all over again. So here, does the 16 go to the bottom?
No.
16 stays on top. What about the 3?
Yes.
That stays on the bottom. And then this x to the 1/3 goes to the bottom, and I'm going to write it as cube root of x. And then this guy, so now we go back up here. So, okay, this guy, so, what's on top for this guy? 1. And then on the bottom, we have 4 or 5 times the 5th root of x to the 4th. Right, and then you go back up again. So, and one more negative. Oh, we got a lot of negative exponents. Okay, one more. And then this guy would be minus 1 over the square root of x cubed. Or you could write x root x, right? And that plus 0 can just go. So I don't care if you simplify your radicals or not. If you leave square root of x cubed, that's fine. All right. Any questions? Okay, it's getting to know you Tuesday. What time do we get out of here? 10:21. We're going to skip this for now. Don't worry. We will do this. But we've got to learn e to the x before you walk out this door. And we have to learn why higher order derivatives. We have 2 very important things. So this one we're going to do together. It's kind of fun. I'm going to give you 20 seconds to write this down. So y equals 2x to the 5th plus x to the 4th minus 3x cubed minus 8x squared plus 10x minus 12. Find y prime 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 prime, or y quadruple prime. Just write down the problem, don't worry. These are fun. Higher order derivatives are fun when the function's a polynomial. Once you get into more complicated functions, then finding higher order derivatives isn't quite as much fun. But it's fun for these. So we'll have fun with this today. All right, as a class, together, I want you to yell out what is the derivative. We're going to do term by term. So what's the derivative? 10x to the 4th plus 4x to the 3rd minus 9x squared minus 16x plus minus 0. Done. That's y prime. Any questions on y prime? So, y double prime, what do you think y double prime is? It's the derivative of y prime. It's called the second derivative. All right? This is the first derivative. This is the second derivative. The second derivative is the derivative of the first derivative, or the rate of the rate. Okay. I'm ready for you to tell me what y double prime is. Ready? Go. 40x cubed. 12x squared. Minus 18x. Minus 16. Yes, sorry.
So what does this tell us?
So in context, the easiest context that we have used so far that you know of is if y represents position, y prime would be the rate of change of the position, which is the velocity. Y double prime would be the rate of change of the velocity, which is called the acceleration. Right? Okay.
What's the rate?
Y triple prime. Oh, I heard someone say it. Someone knows what the rate of change of the acceleration is. What is it?
Sure.
The jerk. Do you know the next three?
No.
You don't? They're fun. Okay, let's do the jerk. Okay, so what's y triple prime?
120
X squared
24x.
24x minus 18. Good, that's a squared. Okay. All right, and y prime 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 or y quadruple prime. So if this is position, velocity, acceleration, jerk, this is called the snap. So, and just so you know, the fifth derivative would be called the crackle, and the sixth derivative is the pop. And that is just because physicists are geeks and they named them after the breakfast cereal. The cereal came first, right? So, yeah. All right, so if you know Rice Krispies, the characters are Snap, Crackle, and Pop. So, anyway. All right, so what's the fourth derivative?
240x.
240x
Plus 20.
plus 24. All right. Okay, notation. So, hang on 1 second. Make these a little smaller. There we go. So I can fit my notation in. All right. This is the y prime notation. If you need to use it in dy dx or Leibniz notation, y prime is dy dx. That's what you know. Those are interchangeable. They both mean derivative. Y double prime is funky. You have to get used to it. D squared y over dx squared. When you see d squared y dx squared, that is the same thing as y double prime. It just means second derivative. The reason that they use this is because this is technically d dx of dy dx, the derivative of dy dx. So mathematicians took that and said, oh, look, it's like d squared and it's like dx squared, and we know there's no parentheses, it's just a notation thing. So anyway, that's how they got it. Okay. And then y triple prime, d cubed y dx cubed, and it just keeps going from there. Yes,
Why isn't the D squared at the bottom?
that's because they chose not to. It's just notation. It's a name. Yes, yes.
I'm just curious, so I know what acceleration measure is in jerk, but what does snap, crackle, or pop measure?
The rate of change of the things that came before them. It's just the rate of the rate of the rate of the rate of the rate.
Do you actually use that in
Physicists must. They gave them names. I don't know. I've never used it. No one in my whole life has ever said, hey, what's the crackle of this, right? Yeah, but, you know. Okay, we got to learn e to the x before the bell rings. We have 1 minute. Thank goodness it's the easiest derivative in the whole world. The derivative of e to the x is e to the x. E to the x is its own derivative. There are only two functions in the world that are this. Y equals 0 is its own derivative, and y equals e to the x is its own derivative. So the slope is the same as the y value anywhere on the function of e to the x. So if f of x is e to the x minus x, let's find f prime. What's the derivative of e to the x? E to the x. And then the derivative of negative x is negative 1. And I know the bell's ringing. I'm just going to do f double prime, and then we'll call it good. The derivative of e to the x minus 1? Just e to the x.
Patter Hall.
All right, good. Go enjoy your day. I am going to do, there's one more example that we didn't get to that I am going to put in the screencast if you want to watch it. It's not a big deal if you don't. Come on, erase. Your one erase. Okay, just going on to the last example. I'm going to make sure somehow, yeah, there we go. Okay, at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x? So we've got some curve, y equals e to the x, and we've got this line, y equals 2x. Now, they don't have to actually be tangent to each other, What they just need to do is share the same slope, right? So we're finding the point on e to the x where the slope of the tangent is the same as the slope of this line. So what is the slope of this line? The slope is 2. So we're looking for a place where the derivative of e to the x equals 2. Well, what is the derivative of e to the x? Lucky for us, the derivative of e to the x is e to the x. So we just have to solve e to the x equals 2. You do need to be able to solve an equation like this. So personally, I take the natural log of both sides. I'm going to write it out, but eventually I want you to get comfortable with knowing that the natural log of e to the x is just x. So if you get e to the x equals 2, that means x equals ln 2. And that's your answer. Oh, and actually we want the point, so the x value would be ln 2. The y value would be
Center East Counseling Office.
e to the ln 2, which is 2. Again, the natural log of e to the x is x, and e to the natural log of x is x. So e to the ln of 2 is 2, and ln of e squared is 2. So they're inverse functions, they kind of cancel each other out. So that would be our point ln 2, 2. If you're confused about why the ln of e to the x goes to x, there's another way you can approach this. You can write an exponential in logarithmic form. You would write log base something of something equals something. The base of the exponential is always the base of the log. The exponent is always what the whole log equals. A log always equals an exponent. And then the 2 is the other spot that you need. Log base e is the same thing as ln. So e to the x equals 2 is equivalent to saying x equals ln 2. Those are equivalent statements. Being able to go back and forth is kind of important. So make sure you can do that. That is it. So just make sure you know how to find a derivative of a polynomial. Make sure you know how to rewrite your simple radicals and rationals, and you know your derivative of e to the x, and have a great day.